Okay, so let's start. This is the last lecture for natural language processing. It's about how we use large language models for not only NLP but also AGI, as I mentioned. Okay, so I will cover the following topics. So first, we discuss in general how we make use of LLMs. Then a part of advanced usage of LLMs called agents. Third, we will discuss reasoning and reinforcement learning. And finally, I will share with you some of the benchmarks we use to evaluate LLMs and how they perform. Okay? And I will conclude with where the field is moving on. First, large language models are actually a new kind of machines in the sense that you program it with the instruction. In the 2010s, I observed that my students have been programming BERT, this kind of pre-trained language models, where the number of lines of code was sharply reduced compared to when I was a PhD student. Okay, I used to code like thousands of lines of C++ in order to develop an NLP software. But with BERT, the coding becomes easier. Normally, my students write hundreds of lines of Python in order to solve an NLP task. Nowadays, you can imagine that large language models interact with people not in code, but in prompts. You give LLMs certain instructions, and they can achieve certain tasks. So prompting LLM is like coding Python. You can draw that analogy. Is it so important? In fact, LLMs are very sensitive to prompts. Okay? So if you ask it in one way, it might give you no answer. But if you ask it in another way, it gives you a satisfactory answer. So people have just found some default or system prompts, the prompt that is not shown to the user by some commercial large language models. And people found that this kind of prompt can go beyond 10,000 tokens. Okay? So which means if you carefully prompt your large language models, you can achieve dedicated result you want. All right. So it is necessary for us to discuss a little bit about how to prompt engineer an LLM. All right. People have summarized a lot of tips. Okay. So these tips are sometimes patient, sometimes careful, sometimes coercing. Okay. So for example, character playing is a very common tip to prompting LLMs. So imagine that you are like a senior software engineer, and now write me a program like that. So with this prompt, LLMs can write better code than without these. All right. So, or you can say you will be penalized if you do this and that, just to stress that something cannot be done. All right. So typically, successful prompts are very specific. Another common way to prompt an LLM is to do trial and error. So if you want to achieve a task, if one round of conversation doesn't work, you do multi-round conversations. And as we saw last week, right, LLMs, they can cope with multiple rounds of conversations by treating all the previous round of utterances as context for generating this round of conversation. So people have found that LLMs themselves can serve as prompt engineers. So, for example, if you give LLM a context, leaving the prompt empty, and show LLM the desired result, okay? You can ask a large language model to fill the blank, okay? Guess what kind of prompt can lead to the correct or the desired output, and LLMs can suggest a list of different prompts to you, right? And with that, you can ask the LLM again to filter, screen, or score these prompts, okay? Or even rewrite these prompts to generate new prompts until you find a prompt that empirically work well, and you can generalize this prompt to more different tasks. Of course, starting from GPT-3, we learned that in-context learning is a useful way of prompt engineering, okay? You can tell the large language model a few demonstration examples together with the input, okay? The LLM will understand your goal better and generate a more relevant answer. In fact, in-context learning can be done by models themselves. Okay, there has been early work, even earlier than the ChatGPT models and other models were widely influential. Okay, so people found that if you try to prompt BART to do a certain task, okay, and then if you retrieve some training instances, okay, consisting of the input and the output, and feed those training instances into the prompt, into the instructions, it can help BART create better results. Another commonly used prompting strategy is in-context learning. And here is an example just to recap. Okay, if you tell an LLM, this is the problem, and solve it. And sometimes it can directly give you an answer which is incorrect. But if you add some instructions, say, let's think step by step. And if you tell LLM the same problem, okay, it will try to answer your problem by giving you a chain of thought, right? And with this, there's more context. And then you can better derive an answer. A different way to trigger chain of thought reasoning is to add a few in-context learning demonstrations, okay? So this is a contrast. So on the left, you just tell it, okay, this is a question, this is the answer. This is a new question, and it will follow your demonstration and give a straightforward answer. But on the right, okay, you say, this is the question, this is the answer, but the answer contains chain of thought reasoning. And this is a new question. It will sparkle a chain of thought reasoning answer from LLMs. Because of this, we also call this kind of in-context learning examples chain of thought prompting. Okay, so you demonstrate the LLM how to answer the question. The LLM will follow your pattern and answer this question. Of course, chain of thought prompting can also be done automatically. Okay, so if you have relevant training data with chain of thought reasoning, all right, you're given a question, you try, okay, to build a model, maybe to cluster the training examples, to retrieve relevant clusters, and to put them into the instruction. And people have shown that this kind of automatic chain of thought prompting will improve the results. All right? And to further exploit chain of thought reasoning, people have developed advanced strategies to do inference. For example, so you can sample multiple reasoning paths, okay? So as I mentioned last week, when you do LLM inference, okay, you can give it a temperature. LLMs will not give you a deterministic answer, but will sample different answers, okay? So similarly, you can do that for chain of thought reasoning, all right? You give it a temperature, you give it a question, you ask the large language model to sample different chains of thoughts, okay? Maybe 3. And of course, these different reasoning processes will lead to different answers. And you can take a majority vote. If 2 of the chains of thoughts lead to one answer and 1 leads to another answer, the answer that the 2 chains of thought agrees on will likely to be the correct answer. Okay, so this is like sampling for chains of thought. And people have exploited this idea further, okay? So if you can sample multiple chain of thought reasoning paths and do the majority voting, why can't you design an evaluator, okay? And this evaluator can be an LLM reasoning prompt, okay? Say, oh, this is the question, this is the chain of thought. Is it reasonable? How likely it is? Let's score it between 1 and 5, okay? So if you take an LLM to evaluate the current chain of thought, you can do search, okay? You know, if you do the sampling, okay, like the third picture shows, it's more like a beam search, right? You sample several chains of thoughts and run until the end, you rank them. But you can do more advanced search, such as best first search, depth first search, etc., by developing a search tree. So when you do that, okay, you can do trace back, and you can do prioritized search or heuristic search because you use an evaluator, right? So this further exploits the chain of thought capability. All right. So by these examples, I showed you how sensitive LLMs are to prompts. And a good prompt engineer can make more effective use of the large language models available nowadays. And people have developed different algorithms to better bring out the intelligence from LLMs, as you saw. So the second topic is retrieval-augmented generation. I have to mention several limitations of large language models, okay? So the first is called hallucination. This term has been well developed in the research of generation. So when people do sequence-to-sequence problems, as I showed you a few weeks earlier, right? So people found that machine translation systems give errors, question answering systems give errors, and they categorize these errors as hallucination. So LLMs can make such hallucination also. And these factual errors can be categorized into 2 broad types, okay? So one is called internal error. So which means the LLMs say things that obviously violates your prompt or the context shown to it. Okay, so or it can make external hallucination, which is you cannot tell directly from the context, okay, or from the text that the thing is wrong, but according to your external knowledge, maybe common sense knowledge, maybe professional knowledge, okay, this thing LLMs give you is wrong. Okay, I often encounter a type of hallucination, which is I ask LLM, okay, about the current research, right? Are there papers talking about hallucination from LLMs? And when answering my question, LLM will list a list of papers to me, okay? And many of them have archive links. And if one paper, the LLM list, have a suspicious archive link or doesn't have an archive link, it might be a hallucination, all right? The title, the authors, the year, the conference are all coined by the LLM. It looks like a paper title, but actually it doesn't exist. So this is a typical type of external hallucination. Also, you know that LLMs requires a lot of time for training because it takes terabytes of tokens to train, okay? And loads of GPUs, thousands or tens of thousands GPUs to train. So LLMs are trained with data only up to a certain timestamp, right? Which means news happening every day is beyond LLM knowledge, right? Or you cannot directly ask LLM for a paper that has just been published to archive, okay, preprint. So this is about timeliness of knowledge. You want LLMs to answer your question concerning the latest news, but LLMs don't contain such knowledge in their parameters. The third is about coverage, okay? Although large language models are trained with extensive data, you cannot guarantee that it has knowledge on everything. Sometimes the data is private, sometimes the data is licensed to a certain domain, etc. And these professional knowledge are very useful, but LLMs are not necessarily trained with them. Okay, how do you solve these problems? Retrieval augmented generation, or RAG, is a solution to avoid all the problems mentioned above. RAG is not a new idea to LLMs. So for sequence-to-sequence models, people have found RAG is useful. Okay, so here is a traditional pipeline for RAG. The first picture shows you the standard sequence-to-sequence modeling. You have an input, you pass it to a language model, you have an output. Okay, maybe you train BART to achieve such tasks. Or alternatively, you have the input, you first feed it to a retriever. It could be a traditional retriever you learn in the information retrieval class, or it could be a retriever we learned in NLP. For example, dense passage retriever, where you have a BERT encoder, okay, and use cosine similarity to match the query with a document, right? And then after you get the reference passage, you integrate the passage and input to an input string, and you train BART to generate an output, okay? And you can also retrieve a lot of different passages, and you can develop a probability model to calculate the answer string. Okay, as I showed you here, right? You use the probability chain rule which I haven't mentioned to you for quite a few weeks, right? But you learned in the beginning of this class to develop these ranked answers. Now, the idea of RAG can also be integrated with large language models, and typically you have this architecture, okay? On the left, I show you how do you pre-process your document. Normally, you have a lot of documents like PDF, a text, web, pages, XML, etc. You first translate everything into text sequences, token sequences. And then you need to chunk them because the document can have varying sizes, okay? You chunk them into segments, and then you use BERT, etc. to embed it into a vector space, okay? And then on the right, if you're given a question, you first turn the question into a query, and then you pass the query into the vector database for your reference documents. And you'll be given a lot of references, and you put the references together with the question as prompt to the large language model for it to do reading, comprehension, and give you an answer, okay? How does it do the reading comprehension? On the right, I give you a sample prompt. Of course, prompt engineer is very important. So you tell the LLM, this is the user query, and I have found these documents to you. Please answer the query according to information from this document, and please do not use information beyond this document, and please be precise and specific to you, etc., etc. Okay? And then the LLM will give you an answer. I have time to tell you the framework for RAG. And over the years, people have developed more advanced technologies to improve your RAG system. For example, query. From the answer to the query, you need a model to do that. You can do query rewriting to ensure that you get more relevant passages. You can do query expansion, which is an information retrieval technique beyond NLP. Okay? Search. Now, the architecture I showed you is a dense passage retriever, but you can use traditional IR models such as BM25, okay, etc., which is beyond NLP. And after search, okay, you get a lot of references. There have been people doing work on using another large language model, okay, or a neural model, trained neural model, to rank these references, okay, to put them in order, or to filter some less relevant references, which cannot be effectively filtered during the retrieval process, because the retriever needs to be fast, okay? So the retriever cannot do deep understanding, but it can use a ranker to deeply understand the retrieved passages and filter them. And there has also been people working on compressing a lot of documents into a summary before feeding that to LLM, okay? All right, about generation. There have been people working on iteratively refining your retrieved document. For example, you retrieve a set of documents, you generate an answer. The answer might or might not be satisfactory. You take this answer and integrate that with the query and retrieve things again. You actually saw this, right? We learned multi-hop reasoning a few weeks ago. Nowadays, RAG systems have been converging to a modularized system. You take the retriever as a module, okay? You take the ranker as a module. You take the generator as a module. And each module, you can integrate new algorithms to refine it. And not only text can be retrieved. Knowledge graphs, as we talked about 2 weeks ago, right, can also be an important source of the retriever. So this is called graph RAG. And also multimodal data, like images, videos, and tables can also be source of the retrieval process. And people have been thinking about RAG on this kind of data. Okay, the third way of better using LLMs is to allow them to process multimodality data, as I mentioned you just now, right? So a very, very typical modality is images, okay? Now, how do LLMs process images? A very common practice, okay, is to turn images into token sequences and then align the image representation and the text representation in an LLM. All right? So the first question is, how do you turn an image into a token sequence? I guess you learn a lot of models in computer vision. And one of the models you learn is VIT, right? Visual transformer. So the basic idea is you have an image which is a two-dimensional pixel matrix, right? And you can cut this matrix into a K by K blocks, okay? And you can use an image encoder to turn each of the blocks into a dense vector, right? So I show you, so you represent this as x1, x2 until xk times k, right? So these are the patches in an image, and each patch is a vector now. And with this basic thinking, now you can do both image understanding and image generation. So the latest technology for image understanding does the image and text alignment in the following 3 steps. The first step, okay, is to make sure that your image representation is aligned with the text representation in LLMs. You tune the image encoder to make sure that they align using some image and text parallel data. The second step is to warm up the pre-trained language model, okay, to work together with images. It's like continued pre-training we learned last week, okay, with images. And the third step is to do instruction following, fine-tuning, okay, by giving the large language model some image understanding tasks. And then use a small amount of instruction following data to fine-tune the large language model. And for generation, it's the reverse, okay? You're given some instructions to draw me an image, okay, where a white dog sits in grass, okay? So grass meadow. So it will generate an image like that. So in order to do that, you need to make sure that the large language model will be able to generate some tokens that can be translated into images, okay? So let's first talk about understanding. You know, you already turned an image into some tokens, x1, x2 until xk times k, okay? And then how do you align this image representation with text representations? Of course, there are a lot of algorithms to do that. But one handy algorithm is just to feed these images to LLMs as part of the instructions. And I showed you. So this is image representation, and you give it an instruction, and afterwards you have a text representation. You can wrap this image representation with special image and the /image tokens, okay? Just to make sure LLMs don't confuse the image sequence with token sequences, text sequences. And then what is the instruction? The instruction could be describe the image. Well, what is in the picture, etc. So these instructions are basically to translate image into image captions or image descriptions, okay? And then how do you train the image encoder? You have to get a lot of parallel data. One image, one caption, another image, another caption. And fortunately, this kind of data is very easy to obtain over the internet. Okay, images with their captions. When you have a lot of these, okay, you can tune the image encoder. But normally, this image encoder will be the original image encoder and then connected with the multi-layer perceptron. Why do you have the MLP? Because you want to change the dimensionality, okay, from maybe VIT to the dimensionality of your LLM. Maybe 768, okay, to map the dimensionality. If you don't have a lot of computational resources, you can directly just tune the MLP because your image encoder is pre-trained on a lot of images, okay? But if you have the computation power as nowadays people do, you can tune both the MLP and the whole image encoder, the VIT model. Okay, so this warms up the image encoding part. And then you can do a second round just to tune a large language model with similar instructions or a little bit more instructions, still over a lot of aligned image and text data. Okay? In this step, you might freeze the image encoder and only tune the LLM so that LLM will understand, okay, what these images are. Or you can tune both the image encoder and the LLM to make them interact with each other. And the third step is to instruction following. Now you have a small amount of data. Okay, this is the image. And in the image, what is the elderly person doing? Okay, or you can ask more questions. So these instructions can be whatever your end task is. Okay. So this is an image. There's an airplane in the image. Is this a commercial airplane or this is a military airplane? This kind of questions you can ask. You fine-tune the large language model with a lot of instruction following data, and you expect it to generalize to unseen instructions. Okay? For example, people have shown that an LLM can answer complicated questions like this. You're given some image that describes some statistics, and you ask it a very downstream question about these statistics. And the LLM can answer your question by understanding the image, extracting the statistics from it, and doing some reasoning. Okay. All right. So about generating image. All right. Draw me a picture about something. How can LLM draw the picture? The key motivation behind is to turn these image patch embeddings into discrete tokens. In other words, you have to turn an infinite amount of possible image patch representations into a finite amount of image tokens. Discretization or quantization. Okay? So a typical way you can do that is you run the image encoder on a vast amount of data, and you extract a lot of patch representations. And then you cluster them, okay, into a vocabulary. You tell the vocabulary size, maybe 10,000, maybe 30,000, right? And over the lots of data, you cluster all these representations into 10,000 clusters, and you take, okay, a representative vector for each cluster. That representative vector could be a weighted average of all these representations, okay, in this certain cluster. And you take this average vector into your vocabulary, okay? We call it a code book or image vocabulary. And when you generate the image, the task of the large language model is easy. It's just to generate a sequence of image tokens from the codebook, okay? And then you feed this sequence of tokens into an image decoder, maybe a diffusion model, if you have learned that in your computer vision class, okay, to generate the image for you. So this is about multimodality. Of course, you say, there are more modalities than images. There are videos, there are audios, there are even tables. There are robotic actions. You know, embodied AI is recently an emerging topic. Okay, it's gained increasing attention. So if you want to control a robot, okay, say, kick that ball, okay? The large language model will translate kick that ball into a sequence of like these joint positions, you know, this way, okay? And then it will be translated into your electronic motor to control the robot. But the challenge of these modalities is lack of data. Unlike images, you don't have a lot of aligned data, okay, between, say, your instruction and robotic actions. So people have developed all these different ways to do that. So one typical way people use is to, okay, use image as a pivot. You know, you can translate everything into an image. For example, sound signals. You can take the sound wave, take a picture of the sound wave, turn that into an image, and then you can translate the image into text, etc. Okay, so I only have time to introduce thus far for you. But I have to discuss LLM agents. So this is a very important way you can use a large language model. Okay. So what is the motivation? You know, you can ask LLM to do a lot of things, to answer a lot of questions. For example, you say, tomorrow I'm going to have a celebration party. I want to invite these friends okay, to my party. What can I do? I will give you a lot of advice, okay? Buy this and buy that. Decorate the party using these kind of things. And write this kind of emails to your friends. But in the end, you have to do it. You have to write the email, you have to buy the things, you have to arrange everything. So if you have function APIs, let's say Taobao, okay, or the Amazon, the LLMs can call these function calls, okay, to buy the things for you on your behalf. If your email has an API, right, LLM can write these emails using SMTP, okay, just to write the email, send the invitations to you. Or if you want LLMs to do a very complicated processing task, such as, can you read a lot of papers and write a survey for me? Okay. LLMs have to read thousands of papers, find the relevant papers, and write a survey. So one RAG system cannot do it because the context size is very long. There are other motivations, okay? You have to allow LLMs to interact with tools or do step-by-step processing, or you have to employ a lot of different LLMs to work together to solve a complicated task. So this is the motivation for developing agent. And agent is an old term, okay? So if you learn artificial intelligence, you have probably encountered the term agent. Or everyone have learned reinforcement learning, right? So agent is a term used in RL. So the traditional sense of agent is an autonomous system, okay, that can reason, make decisions, and do actions on your behalf. So this is a very classic definition of agent. And now there has been debates on the difference of agent and agentic systems, which I do not want to involve into this classroom. But we can list a few key features of agent. And the top two is you have to reason and make decisions. So this is one important feature of agent. And you have to act on the user's behalf. This is the second feature of agent. There are other important characteristics. For example, you have to observe the atmosphere. If you have embodied AI, you have to observe the physical world, for example. If you have a programming AI, you have to observe an existing project, and the code, etc. Planning. You have to break a complicated job, such as arrange a celebration party into steps, different subtasks. And you have to arrange the execution of these tasks. Collaboration. The agent can collaborate with a lot of other agents. And self-refining. You have to continuously learn and improve yourself according to user preferences. All right, so these are the key features. And this is the architecture for LLM agent. Of course, LLMs have taken the role of the brain for modern agent. Okay, most of the agents are driven by LLMs. The user will interact with the LLM, and the LLM will perform a lot of tasks by planning, reasoning, okay? Using tools, okay? And keeping track of action history and other things in a memory. So these are the most important characteristics of a current LLM agent system. All right? Let's first talk about tools. Tool using is not a characteristic of LLMs. In fact, the people have done research on tool using in sequence-to-sequence learning. Okay? So this is a representative model. Again, it's done with BART, etc. So the first picture shows you the standard sequence-to-sequence BART. Okay? You train it by fine-tuning it with tasks, input and output. But then, to answer specific questions, you might want the system to retrieve relevant knowledge by using external tools, such as search engine. Okay? So, to do that, you train BART in a different way. Okay? Like the second picture shows. So rather than directly answering you the question, you allow BART to generate the orange thing, okay? So the blue thing is the prompt, the question. And then the orange thing is what BART generates. Rather than directly the answer, say, I call the weather engine to get a weather, okay? Or I call the search engine to retrieve some documents. And once the orange part is predicted, BART will stop there, okay? And the system will feed that to an external engine to get the dark blue part, okay? And then this dark blue part will be concatenated automatically to the string. And the string will be further given to BART to produce the final answer. Okay, and if you train BART to do this process, it will give you the answer correctly. All right? So when LLMs are popular, so people have developed different ways to create training data in the previous process. Okay? So you can turn question and answer data into tool usage data by replacing some parts of the data with the tool call. Okay? And then you collect a lot of such training instances. You can train your sequence-to-sequence model to use all different kinds of tools. And nowadays, LLMs are trained to use a lot of typical tools, such as the search engine, the calculator, the email system, with a JSON interface. Okay, JSON is the programming language. And then, now back to LLM agents. If LLMs can use tools, okay, then they can perform a complicated task by a sequence of tool calls. And this is a planning process, okay? You say, you're given a task to LLM, prepare a celebration party. The LLM will say, okay, I use tools to invite the first guest, invite the second guest, invite the third, fourth, okay? And then you say, I go to Amazon and buy A, buy B, buy C, okay? Food, decoration, gifts, etc. And here I give you an example. And suppose that you tell, okay, the LLM, there are such functions you can call. You can get the time, get the weather, find a restaurant, and call a calculator. In your prompt, okay, you tell LLMs, these are the functions you can call. And then suppose that a user came, say, okay, is tomorrow hot? If the tomorrow weather is not too hot, okay, then I want to invite some friends to a restaurant. I want to find a dumpling restaurant, okay? I have 3 people eating, but I only have 150 yuan. So dumplings, find me some restaurant, okay? So after receiving this, the large language model will first check the weather by calling the weather engine and get, okay, the weather is not warmer than 30 degrees Celsius. So I get where you are, and let me find some restaurants with dumplings, okay? And then the restaurant ratings are there. They want to filter the restaurants with high ratings, and the price are there. So you calculate 3 people with a budget, okay? This restaurant satisfies the requirement. It will tell you, okay, tomorrow you can go. These are the restaurants, and these are the distances to you. So this is a typical agent use, okay? There was a system called AutoGPT, which does something similar to that. It was very popular 2 years ago. But now let's come to planning reasoning. The agent can take complicated steps to reason smarter, okay? So, for example, the LLMs can take one action, okay, and get some environment feedback, and then think, do the reasoning. And this is to, okay, so on the left is a question, okay, on what is a product that makes use of this Apple, what kind of alternatives you can use for like Apple remote control. You have to first find some applications that makes use of the remote control. And when you search online, they give you an answer front row, okay? And there are a lot of different products named front row. And you have to think, okay, which is likely the product. And then after you think and do the thinking, you execute the next step, okay? So this is like you do an action and then you do the planning. Do another action, you do another planning. So this is a framework. Or there's an even more complicated framework. So you do an action, you observe, you do the planning, you do another action, observe, and do another planning. But after you get an answer, the answer can be wrong, okay? So if this answer can be verified wrong, okay, the system will take the whole process earlier, okay, and then reflect by itself. Okay, I did something. it was wrong. Why did I do it wrong? Oh, maybe I did one step incorrectly. Okay, let me take this lesson and re-execute whatever the steps before. So think, do, observe, think, do, observe, find the answer, check, and summarize. Bitter lesson, I do the steps again. So this is called reflection. And actually, people found that the reflection is actually a long, short-term memory thing. Your current steps are your short-term memory, the context. And if you had a failure, okay, you think over the failure, you do a summary, this is a long-term memory. Okay? You summarize the past failures. And people found that this kind of a self-iterative refinement process is like reinforcement learning. But it's not real learning, okay? No parameters are updated. It's just that the lesson, the reward is a text. So the bitter lesson summarized by the LLM itself is a reward to the whole agentic system, you know, and it can perform better. All right, I gave you a few examples of agent systems, and now, really, people are very excited on agent systems because people really take LLMs as machines, you know. You have the new computer, you have the new machine. You can do a lot more than your traditional computer. And how do you put these computers together to solve end tasks, like in finance, in law, in programming, etc.? So people build a lot of such agent systems. And people have used multiple LLM agents to achieve complicated tasks. I'll show you an example later. But now, what are the key things to the success of using agent? There are two things. First is how do you put LLMs together into a framework, infrastructure. This is called scaffolding. Okay? The structure of your agent system is very, very important. As I showed you, React, reflection, or even complicated structures. The second is, again, prompt engineering. How do you tune your prompt? It's like how do you code a machine, okay, to make LLMs work cleverly. So there is a complicated agent system to do software engineering. The user might ask the system to do a complicated software engineering task. And in the agent system, there are product managers, okay? There are like software engineers. There are system architects. Lots of different LLM roles. And then they work together, a lot of communications and a lot of programming. In the end, they deliver a product to the user. So this is a multi-agent system. You know, we have also worked on multi-agent systems to write you a paper survey, for example, or even write you a full paper. So LLMs can do a lot of complicated things. So in this part, let's discuss LLMs and reinforcement learning. Why do you want reinforcement learning with LLM? There are at least two major motivations. The first is to align your language model with human preferences. So we touched upon that last week, RLHF, okay? But I showed you last week that RLHF can actually be done without RL because your language model is implicitly a reward. Okay, so you can use algorithms such as DPO to align. So the second reason is you want to enhance the reasoning capability of large language models. Okay, so if you have a verifiable reward, what is a verifiable reward? For example, if you do a math question, you can verify if it's done correctly or not. Okay, if you do logical reasoning, in the end, you can verify whether you obtain the correct answer. So RL with verifiable reward can improve the reasoning capability of LLMs. And this has been shown to largely improve the quality of answers. But there are other uses of RLs. I didn't have time to mention LLMs with machine translation in particular, but people have been using a lot of parallel data to fine-tune a larger language model to do machine translation. And then after this process, they can use reinforcement learning with an automatic evaluation metric as the reward, okay, to align a large language model to conform to that metric or to translate more naturally. Okay, so no matter what, so we have to discuss some mathematics, how reinforcement learning works with large language model. And here I will use two RL algorithms to illustrate. So first of all, you have all learned reinforcement learning, but just a recap, an agent will interact with the environment and get some reward to improve itself, okay? So this is a Markov decision process. So you start from an initial state and take an action, you change the state, you take another action until the end, final state, okay? And the goal is to train the agent to explore a path with the maximum reward. So this is RL. So corresponding to a large language model, the large language model is the agent or the policy model, okay? And every action is a token. Every state is a context, okay? So when you generate a token sequence, you take one token, second token, third token, until the full sequence is done. So the first algorithm is PPO, Proximal Policy Optimization. This is the algorithm used in the OpenAI's RLHF task. Okay, so the goal here, okay, is to maximize the total reward. Okay, so suppose we have a set of data. Okay, so the data we collected with human preferences. Okay. And we have, remember, we have a reward model. We've trained a reward model to generate the rewards. So you want to maximize the expected reward. Okay, so this is the objective. But then you also want the model not to be changed too much from your fine-tuned model. So I add a second term to the objective function. I also want to minimize the KL divergence between the new model distributions and old model distributions, okay? And you know KL is also an expectation, right? So if you put the KL term inside the expectation, it's also the logarithm ratio between the two models. I think we use that for DPO, but we don't need to explore more for this part, all right? So for PPO, there are a few models, like a policy model, so which is the LLM to be trained, a reference model, which is the instruction-tuned version of this LLM, also a reward model, which is what I described with you last week, okay? And because PPO is also an actor critique machine learning algorithm, it also has a critic model, which I'll introduce to you later. Okay, so if you look at the algorithm, the policy model or the model to be trained, okay, generates a token sequence. So every action is a token. And therefore, we can break the total reward, okay, the capital R, into a step-by-step reward, lower R. R1, R2 until the last step. And the goal, okay, is to maximize the expected reward over all possible sequences according to the language model. Here I call the language model pi theta p, okay, which is slightly different from last week. I call it p y given x theta p. Okay, so this is the goal. And you know, with this goal, we can use stochastic gradient descent, but this is an objective function to maximize, so we use stochastic gradient ascent. But no matter what, we have to calculate the gradient, which is like this, okay? So the expected reward. And we take the derivative with respect to theta p, or the large language model. Okay, so if we expand this expectation a little bit, we can turn this expectation. So if we expand this gradient, okay, this gradient is a summation, right? So we could turn this summation into an expectation. So you know, an expectation is a weighted sum. So currently this is a sum, the sum of all possible y sequences, okay? So the reward of this sequence and the derivative of the probability, sequence probability with a parameter. So if we turn that into a weighted sum, I want to multiply this every term with a model probability, okay? Then how do we do that? We can expand this equation by having a model probability divided by model probability. So this is 1, right? So I take the numerator to the weight for weighted sum. How do we deal with the denominator? So the denominator is actually can be combined, you know, the denominator can be combined with this derivative, you know. What is this? This is actually the chain rule of the log probability of the model, right? So I then get this equation. So it's an expectation of the reward times the derivative of the log probability with respect to theta. Okay? So this is the new equation. Okay, so this is equation to for the gradient, but this is an exponential sum. I cannot calculate that in tractable time complexity. So how do we do that? And people typically do the approximation, okay? So you can't do the expectation, but you can do sampling. With a lot of samples, when the number of samples increase, you approach this expectation. Okay, so typically you do 4 or 8 sampling. Okay, it's already sufficient. So you turn this expectation into a summation, okay? 1 over m, the sum of each sample, the reward times the log probability derivative. Where is the probability term gone? It went into your sampling process, okay? All right, now let's turn this total reward into a step-by-step reward. You know, so this is the sample, okay, the total reward. And you know, each total reward is a sequence, right? So LLM is an autoregressive generator. So in the sequence, every step you have a smaller reward, Ri. And then you have the model probability now. Okay, because it's an autoregressive model, the model probability is current yi given x and y smaller than I. So that's the real model. So you have to accumulate these gradients. Okay. Okay, now you have a R, which is the reward. How do you calculate the reward for every step is the question. If you have a reward model, okay, like ILHF, the last step, you know, when you finish the whole sequence, you generated a sentence. Now, you should give up serving, period. Okay, when you generate this period, this sequence is done. The last step has the reward model calculated reward. This is probably a negative reward. It's not informative, it's not encouraging. Okay, it's not patient. But the previous steps, the R are all zeros because until you finish the sentence, I know your meaning, right? Or you might just change your sentence. You should finish your serving. Or not? Of course not. Okay? So you should give up serving or not? Of course not. So without finishing the sentence, you can't determine the meaning. Or if you are verifiable reward, okay, then you don't need a reward model because your answer can be verified, correct or incorrect. Okay, in this case, if it is a correct sequence, the last step reward is 1. All the previous step reward is 0 because you haven't finished it. If it's incorrect, then for every step, the reward is 0. Okay, now it's viable because I got the R for every step and I have the gradient. Okay, I can just put this gradient into SGD. I can train a model. But, you know, this is like policy gradient. You all learned that, right? It's not easy to train. For example, because your R is not stable, right? Your samples are not stable. Sometimes you penalize a good, sometimes you reward to a not so good output sampled here. So how do you solve the problem? You have to take the relative advantage, right? So how do you do that? You calculate the Q function or the expected future reward. You call it a return, right, in reinforcement learning. You calculate the Q function for an action, for the next action, and you also calculate an expected value, a value for current state, or the expected return for the future actions from this state. And you use this Q minus this V, the Q function minus the V value as the advantage. Now, this advantage is more stable in training because it's a relative return, a relative advantage for the action you take. Okay, so you turn this gradient into this gradient. Now you introduce an advantage function, right? So you have 8 samples. For the 8 samples, for every step, you take the log probability of the model times the advantage for this token. Then, how do you estimate the advantage? You know there's a method called generalized advantage estimation, right? How do you calculate that? You calculate a lot of these delta functions, okay? And at each step, the delta function is the R, the reward for this step, times, plus the next step, the value, minus this step value. So this is a delta function. The advantage for this step can be estimated as the weighted sum of all future delta functions, right? So this is the GAE. What is lambda? Lambda is a hyperparameter for the decay, right, of future reward. I don't have time to elaborate, but I assume that you are all familiar with GAE. If you're not familiar, just take my equations for granted, okay? So now here, when you have the value, you can introduce a value model. You can introduce the value model to estimate the values. And also, because you're doing a weighted sum, right, of all the future delta functions, okay? Although you only get a reward in the last step, you have an advantage, non-zero advantage at every step. Because your last step reward will propagate to your previous step advantages, right? So let's flip back to the previous slide. if you use this equation to train your LLM, you don't have stable training because only the last token will get gradients, right? But you use this equation, every step you have gradient because of non-zero values here, right? The weighted sum of delta functions. Okay. Now I have to discuss the value model. The value model, is here to estimate the value of each state. So for calculating the advantage functions, okay? So the value model is another language model to calculate the values of yt given x and y smaller than t. And I use theta v to represent the value model. And the value model is actually trained. It's the critic model, right? It's trained together with the policy model. So in PPO, you train 2 language models rather than 1. Okay? And you use 4 language models. The 2 that are not trained are the reference model and the reward model. Reward model is trained, okay, as what I discussed last week. And the reference model is the model after instruction tuning. So you have 4 language models in PPO, and 2 of them are trained. One is the policy model, and one is the value model. How do you train the value model? So basically, you train the value model by minimizing, okay, the sum of all these advantages, okay? So it's like a mean squared error loss function. All right, to align the value differences with the reward values. Okay. Now, this is basically the structure of PPO. But there is, again, something I have to mention, which is, okay, you have sampling, right? You use a language model to sample 8 sequences. And then you tune the language model using the advantage times the log probability loss. But after you tune the model, you do the second sampling. You have to use the new model, so which is very inconvenient because you want to do batch level training. You want to use the same model to sample the 8 sequences in the same batch. Okay, how can we do that? So there is a technology called importance sampling. Okay, so if you use one model to take samples, okay, on behalf of another model, okay, you can do importance sampling. So the idea is, if you use a model P, okay, to sample for an expectation of a distribution Q, then I can take this derivation, all right? You introduce P by adding P divided by P into this expectation, okay? And then you turn an expectation over Q into an expectation over P, and then with the term Q divided by P. So this is called importance sampling. And so how do we apply importance sampling to the PPO training process? It's like, before I train a batch of samples, okay, I use the model before I fine-tune it to sample a lot of samples. But then I gradually tune the new model, right? I gradually tune my LLM. So, but my samples are sampled by the LLM before I tune it in the batch. So to adjust this difference, I have to take the probability divided by the P owed, okay, as an important sampling term. So the new, okay, in summary, if I sample all these training instances over my batch using a model, okay, the model parameters, before I do the fine-tuning in this batch, then I train the LLM. I have to add a factor to my gradient. And this factor is the importance sampling ratio. Okay? And after that, I can use an old model to do the sampling and keep on adjusting parameters for my model. Okay, you only need to add a ratio to my gradient. All right? Okay, there's even one more complication. So adding this ratio does not guarantee stable training at all. Okay? So you have to think about some strategies to stabilize training. For example, you can use KL between the two models, or as OpenAI does, you can simply clip the gradient. Okay? What do I mean by clipping the gradient? It means that if the ratio, okay, and the advantage doesn't satisfy certain criteria, I will discard this sample. I will not update my model. Unfortunately, I don't have time to explain the reason, okay? I can tell you one simple idea, which is if you don't discard some samples, your RL will not be stable, okay? This has a very deep root in the history of RL research. But what kind of samples do you want to discard? First of all, if the advantage is positive, okay, positive sample, but if the ratio is large, it means you want to award the sample very richly, okay? This will cause instability. You'd better discard this sample, okay? The second is if the advantage is negative, you want to penalize the sample, okay? And if the reward is very, very small, okay? Very small penalize, okay? You'd better not to penalize this sample at all, discard it, okay? So there are two criteria. Okay, so you know the threshold is on 1 plus epsilon and 1 minus epsilon respectively. And this epsilon is typically 0.2, okay, for reinforcement learning. All right, in summary, I added a ratio to my gradients, okay? And I use this ratio to discuss a lot of samples that doesn't meet a criteria. And then my training will be stable. All right, so given this training process, can we reverse engineer a loss function? The answer is yes. If you reverse engineer the thing into a loss function, it will become a function like this. I don't have time to explain you in detail. Okay, it's a minimal function. So let's skip the proof also. There's a proof. Okay. Let's just take the derivative of this minimum function, non-differentiable, into two subgradients. And in the case, okay, it satisfies the slope subgradient. It will be exactly my clipped gradient. In other cases are my discarded samples. The gradients are 0. Okay, I can prove back the reverse engineered loss function leads to the same gradient calculation than before. All right, but let's forget about it. Let's just summarize PPO. So the PPO objective is to maximize the reward of your LLM, okay, while minimizing the KL divergence of your LLM and the fine-tuned LLM, okay? So you have two loss functions, one for training your original LLM, one for training a critic model to estimate the value of each state. All right? And then how do you the optimization is very easy. You just use your current LLM to take samples, take a lot of samples, and then you do a batch SGA to update the model with this ratio, okay, and discarding criteria times the advantage function times the gradient for the log probability of your LLM. And this advantage is calculated using your value model. All right. 4 models, right? Reference model, reward model, policy model, critique model. Policy model is the LLM under RL. And then this is the reverse engineered loss function. And my equations are not so rigid because I used pi-o. This pi-o is applied in the training dynamics, you know, but I take it as an overall loss function. Okay, PPO is time-consuming because you have 4 LLMs in the training process, and you have to update a value model. So there's a simpler version, which is more efficient, requires less GPUs to train. It's proposed by DeepSeek in the training of the famous DeepSeek R1 system. It's called GRPO, Group Relative Policy Optimization. Okay, so the difference between PPO and GRPO is like this. So in PPO, you know, you sample a lot of sequences, and you want to take the gradient from these sequences to update your LLM. And in the end, you train a critique model, right? To give you an advantage. You use this advantage to weigh each sequence gradient, log probability. A GRPO is very simple. You also take 8 or 4 sequences, samples, okay? But you forget about the value model, forget about the critique model. You just let the 8 compete with each other, okay? To calculate the relevant advantage for each, and you're done. So how do you compete with each other? You know, you have 8 sequences, and each sequences, if you have a verifiable reward, or if you have a reward model, you can assign a last step reward. And this last step reward will be the final global reward. Okay, each sequence has a global reward. And with that, you can calculate the mean of the 8 sequences, the mean reward, and the standard deviation over the 8 sequences, right? And the relative advantage is simply the current sequence reward minus the mean divided by the standard deviation. And that's the advantage, okay? And the advantage is for the whole sequence. You know, weight, when you have a critique model, you have an advantage on every token, right? Every token has a different advantage. But now you can only calculate an advantage for the whole sequence. How do you apply this advantage to each token? The answer is simple. You just copy the same advantage to every token, and you're done, okay? You no longer differentiate good tokens and bad tokens. You only differentiate good sequences with bad sequences. So this is a contrast, you know. For PPO, every step, you weigh the log probability gradient with token level, A. For GRPO, you weigh the gradient with global A, and that's it, okay? You see, this is too coarse-grained, but it turns out to work very well, okay? But just like PPO, you do gradient clipping as well. That's it. All right. Let me summarize, okay? I introduced 2 reinforcement learning algorithms to you. These 2 are the 2 maybe most discussed reinforcement learning algorithms for LLMs. And they share a lot of things in common, right? They're all policy gradients. They all use advantage to update the model. They all are simple because you only need a few samples. and then you just train the LLM just as you do the SFT, okay? GRPO is even simpler than PPO because you just calculate an advantage and you use it to weigh every step. And it turned out that using a verifiable reward, okay, you train the model can become very smart in reasoning. Not only in math questions, but also in general language understanding problems. You know DeepSeek R1, and you know OpenAI O1 and O3. And there are a lot of other models currently following the trend to do RL over verifiable reward. The final section introduces the evaluation. You know, we are an NLP class, and in this week, we've gone beyond NLP, right? Into coding, into math, a lot of different problems. But let's move back to NLP. Why do you introduce LLM? Has LLM changed NLP? Okay, so let's first look at a range of natural language understanding tasks. So this task has been very popular 3 years ago. But now they are no longer popular. Why? Because, you know, in the old days, people have been fine-tuning BERT and BART and GPT-1 to do things like this. And people have achieved this level of accuracies. And now, using GPT-4 without fine-tuning, and maybe with some ICL, and you get this level of accuracies. So it's a killer across the board. So people no longer work on BERT and BART, okay? There are some open source large language models, such as, you know, QWEN, and Llama, and Mistral, okay? Which some of you use in your projects, okay? For natural language generation, things are similar. So people have been working on machine translation, text summarization, open question answering, etc., right? So, and if you look at large language models, they perform better than traditional models, okay, for most of these tasks. And people even found that some of the evaluation metrics we discussed in week 2 no longer work, because LLMs are so much like humans that human evaluation is necessary. So, LLMs killed NLP? No. Actually, there are some NLP tasks that LLMs don't solve very well. What are they? The most representative part are structured prediction tasks, okay? I squeezed your term and left only 2 lectures for structured prediction. Remember HMM and CRF, and also neural structured prediction. But these are still the most effectively solved by BERT, okay? And the lectures I showed you earlier. LLMs turned out not to be so sensitive to structured. Maybe mostly because the structures are very subtle, and it requires a lot of standardization and annotation. And it requires a lot of protocols. LLMs, although they can guess the meaning, they cannot follow exactly what human requirements on the formats are. So people have tried to turn structured into programs, because LLMs are good programmers, but they don't work very well. So the current state of the art is to combine the strength of LLMs and BERT models to make a multi-agent system to solve these tasks. So NLP is still alive to some extent, but NLP researchers have merged into machine learning researchers and computer vision researchers and embodied AI researchers. So basically, every subdiscipline of AI have turned into LLM. Okay, and you don't see clear boundaries between these disciplines anymore. And LLMs have been evaluated on tasks beyond language understanding and generation. And here is an example. LLMs are frequently evaluated on math tasks. Okay, so this is elementary school mathematics. So I think 4 years ago, we've been doing research on that. But soon in these years, these questions cannot challenge LLMs anymore. And people have moved to high school mathematics. Okay? And soon this cannot challenge LLMs anymore. So people have moved to national and international mathematical competition questions, contest questions. And even professional mathematics questions. And these are roughly what LLMs can do. For math, for elementary school math, for high school math, LLMs doing very well. For contest math, are doing pretty good. Okay. For professional math, LLMs are improving. Logic. So in addition to mathematics, you can answer logical questions. For example, Logica, okay, it's a reading comprehension task. Okay, it asks LLM to reason before it can choose the correct answer. A proof writer is another task. It gives you some statements and ask the model to find a proof by making use of this statement. Folio is a logical reasoning task. It asks the LLM to perform reasoning or perform formal logical reasoning. Rule taker is also a logical reasoning task by asking LLM to make use of rules to reason. And AR-LSAT is a reading comprehension dataset, just like Logica. It uses some law dataset, examination dataset. And control is a logical reasoning dataset made in form of natural language inference. So these are still NLP tasks, but they test the reasoning capability of LLMs. And currently, LLMs are performing better and better, okay, competitive to humans on this kind of logical reasoning tasks. And people have also devised very comprehensive tasks on different kind of programming, NLP, and logical reasoning tasks, such as the Big Bench. Big Bench contains 200 different tasks. And here are some example tasks ranging from mathematics to common sense reasoning to logic, etc. And Big Bench has a light version which contains easy questions. But people found that LLMs soon conquer these questions, and they developed a hard version, Big Bench Hard, BBH. And soon LLMs are conquering these questions also, and people have developed Big Bench Extremely Hard, BBEH. Extra hard. So you can see that LLMs are improving on these tasks as well. Okay, so these are math and reasoning. These are abstract challenges. Okay, but they are already beyond NLP. There are even things more beyond NLP, which requires professional knowledge and skills to solve. There is a dataset called Massive Multitask Language Understanding. So it contains science questions, social science, humanity questions, all these kind of questions. So for example, this is math, very easy to understand. This is high school history. Okay, because this is US history, I cannot answer the question. I don't know who of you can answer the question. Okay. People had just gone Gaokao, right? a day ago. It's a very important social event. And there are law questions, okay, international law, different professions. And look at how LLMs are performing. They are dominating these data sets. They have widespread knowledge, better than any human being, at least better than me, I think. Okay, I just mentioned Gaokao. Actually, there are data sets with Gaokao questions. This is called AGI evaluation. And people are using high school knowledge, okay, to question LLMs. But LLMs are soon dominating these data sets. They're approaching human level. So if high school questions cannot stop them, what kind of questions can we use to evaluate them? Of course, postgraduate questions. There is a graduate level Google proof question and answer benchmark, which are taken from examination questions. Biology, aerophysics, chemistry, etc. I cannot answer all these questions, but LLMs are giving at least answers that pass graduate level examinations, right? Just like you want to pass my NLP class. I did give my questions to GPT-4, and it can answer all of them correctly. Okay, some of you must have known that. I see that from your smile. Okay, in professional skills, there are also a branch called coding, you know. You give LLM a coding with the prompt, how do you want the function to perform, and LLM can actually finish your code for you. LLMs are doing very well on these questions, and people are thinking about harder questions. How about debugging? Okay, we humans make problems. Let's make a comprehensive data set for debugging on code. So this turns out to be a challenge for LLMs. LLMs don't perform very well. But there are even more complicated challenges to LLMs, such as you're given a paper. Try to write code to reproduce answers in these papers. LLMs are performing badly in these tasks. Okay? Papers are not so reproducible. Okay, it's not the fault of papers because in this benchmark by OpenAI, all the papers can be reproduced. It's LLM's fault. Okay. Finally, safety and security, ethics, social are very important for LLMs. There are dedicated tasks to ask LLM, is this content toxic? Okay. All right, is it violent? Does it contain discrimination? Does it contain danger? Etc. Okay. They ask LLM to decide whether the content are toxic. This is a very important question. And LLMs are improving, but they are not very secure. You know, there are constant news about people hacking LLM to give them knowledge on how to make nuclear bombs or dangerous chemicals, etc. And of course, there are security data sets on different brands of professions. For example, medicine. Okay. You don't want to put a patient in danger. Okay. And there are questions on medical science, and LLMs are also improving in these areas, and this is an important area of research. Similarly for agents, right? You don't want your agent to steal your private information. You don't want agent to write dangerous code, all right? You don't want agent to harm your mental health, etc. So there are benchmarks to evaluate agent safety, and LLMs are improving in these benchmarks also. Finally, LLMs are constantly improving. Why do they hack these benchmarks? Because every time you release a benchmark, LLMs will take the data and integrate the data into its training set. So the next release will conquer the data sets. How do you solve the problem? So people have developed different solutions. One example is Chatbot Arena by Berkeley University. So this arena asks users to use LLMs, okay, and to rank LLMs. The basic idea is the user is given an interface, and he can ask any question or choose a predefined question. And then the system will give you two answers from two LLMs. It will not tell which LLMs are, but it will ask the user to choose which one is better. Okay? And by that, it can rank LLMs by using some like sports tournament metrics. For example, you have a lot of wins and losses. Now it can rank the players. It can rank LLMs with real users. Okay. A second strategy is, for example, Helm. So this is an open structure that allows you to insert new data set into it. Okay. You have constantly upgraded data sets, and you periodically rank all the LLMs on all these data sets. Okay, so 1 month you release a ranking. The second month you release another ranking. So you avoid LLMs from leveraging existing data to improve the results. Okay, there are other methods, such as counterfactual. So you have a release data, you don't mind. You use some automatic tools to change the named entities to make this data some alien names. You can also ask LLM to read this data and answer questions, new questions. There are other considerations when you evaluate an LLM, such as the speed. Okay, how fast does it take? How much time does it take to generate the answer? The latency, how much time does it think before it gives you the first token, or the cost for commercial LLMs, okay? Okay, so I can conclude this week and conclude this course. So I showed you through the history of NLP research, especially machine learning history, okay? I showed you from simple counting algorithms, which some of you actually did in your projects, okay, to complicated features and discriminative models, to neural nets, to pre-training, and to LLMs, okay? It took the whole field maybe 20 years to evolve from statistical models to neural models. And maybe 10 years to evolve from neural models to pre-training. And maybe 5 years from pre-training to LLMs. And now 2.5 years have passed. I think that the evolvement of this field is very fast. And LLMs have conquered most NLP problems. And LLMs have made different subdisciplines of AI converge. But there are still many problems LLMs cannot solve, such as multimodality or some very dedicated tasks, such as professional math, etc., and complicated reasoning. Overall, all in all, they don't generalize as well as humans, okay? There are a lot of things LLMs can do, but humans cannot do. But there are many things humans can do, LLMs cannot yet do. All right. So people have suggested artificial general intelligence and artificial superintelligence. But all of these things are happening all together. Okay. I think the future development of NLP field and LLMs are to help them solve tasks humans can solve, but they cannot yet solve, which is generalization and stable, explainable processing of complicated tasks. And of course, during this development, we need to pay special attention to AI safety. Okay, so this is a very important topic. To summarize, in this week, we have learned how to use LLM, prompt engineering, and how to do agent. Agent is a future direction. We've learned how to make LLM reason with reinforcement learning, and we've learned how people evaluate LLMs. All right. With that, we conclude the whole course, and I will see you later. Okay.